All right, record and resumed. Here we go. All right, so we're doing rotational dynamics. This is unit 7 by AP's book. And this is a poster you guys have seen before. You guys saw this a few weeks ago when we did some rotational stuff. We were doing like centripetal force and stuff, and I thought it'd be a good idea to introduce you guys to some rotational stuff. You guys remember like the turntables, that kind of thing, right? Uh, you guys should know the top half of this poster, right? And then the bottom half is kind of new territory. So I'm going to take a few minutes to review some stuff that you guys have already seen, like rotational kinematic motion, like turntable type stuff, right? And then later on, we'll get into the bottom half of this, which is going to be new stuff, right? So see these variables here. There's linear motion on the left, rotational motion on the right, right? So like analogous equivalent, right? And a lot of these kinematic variables, like the first 4 rows here, think about like a turntable turning, right? Like a turntable, right? So time in seconds is still time in seconds, right? Instead of saying how far in meters, we're going to measure how far has the turntable turned, right? Which you could use a protractor for, except a protractor measures in degrees. And do you guys remember what is like the more pure mathematical way to represent angles? Not degrees, but radians. Yeah, radians, right? 1 radian about 57 degrees, or if you like 2 pi radians in 1 revolution. Got that? Instead of saying how fast is something going like miles per hour, meters per second, right? Like a car speeding up or slowing down. Never saying this turntable is like speeding up or slowing down, rotating. So it's like radians, or sorry, this turntable is spinning its own speed, right? Called an angular velocity, right? So it's a Greek letter omega. You quantify that in radians per second. Like the Earth right now is turning at some constant number of radians per second. Right? So 24 hours in a day. Right? And then the turntable could be speeding up or slowing down. Right? It's kind of analogous to a car speeding up or slowing down a straight line, but this is a turntable, right? So that's alpha is angular acceleration. That's radians per second per passing second. So it could be radians per second squared. It could be speeding up or slowing down, right? You might remember too that you can connect angular motion back to linear motion by simply multiplying by radial distance from the center. So here, what if we're up in a helicopter looking down on a merry-go-round? Here's a merry-go-round. There's like 3 friends. They're flying around on this rotating merry-go-round, right? 3 friends, right? Now the kid in the center, he's not really going anywhere. Like, what's his distance due? Well, it doesn't matter how fast or like how far it's turned. Right? Multiplied by 0, it hasn't gone anywhere. Right? Same thing with how fast. If you point a radar gun at him, right? Doesn't matter how fast the thing is spinning. He still has 0 linear speed. Like if you point a radar gun from the outside. Right? But what about his friends? Like the further out you are, scale it up by this radial distance r, right? You'll be going further distance and also faster, like meters per second. And then acceleration is a similar type story that's speeding up or slowing down, rotating. Okay? Okay. And then all that kinematic stuff, all these kinematic variables, oh, they also have these three equivalent rotational kinematic formulas that apply to them. The original ones you guys saw way back in like August was like x equals v naught t plus half at squared, and then a couple other ones. And the new versions like beta is omega naught t plus half alpha t squared, and so on, right? Okay, so that's all reviewed. We did do all this back in the day when we were doing like Unit 3 stuff. But by AP's book, this is all actually part of Unit 7. I thought it was a good idea to introduce you guys to all that kinematic motion back in the day anyway, because this whole Unit 7 is kind of like everything we've done times 2. Like everything that had a linear concept now has like a rotational equivalent, right? For example, these rows down here, right? We got mass measured in kilograms that could represent how much matter, but also how much inertia has them, but only like in a straight line. In a rotational sense, it's not exactly that straightforward. That's one of the first ones we're going to look at. Newton's second law of motion in a straight line has this rotational equivalent called torque. There's a rotational equivalent for momentum and for energy. Right? So as far as we can here. All right, you guys ready to get new stuff? New stuff? Right. Oh, actually, this one sort of new one. I did plant this idea back in the day. There's remember these 2 meter sticks I was passing around. I was saying like if you're blindfolded and picked them up, okay, they feel like the same mass, the same weight, but if you shake them back and forth, right, the only difference is like where the masses are like located. One where they're close in, has hardly any inertia at all in a rotational sense, so you can rotate back and forth with those. But the one where you just slide the masses out, right, you haven't changed the mass of the weight. What you have changed is the location. Now it's a bunch more inertia in a rotational sense. It's really hard to change the state of motion, right? So the formula for that is mr squared for a single point, right? And then if it's multiple points, you just add them up. That's what the sum of is, right? Sum, just add them up, right? So if you ignore the meter stick itself, or say the meter stick has negligible mass, and just focus on these 2-point masses, right? That's mr squared plus mr squared. That's like 2mr squared for the left one, right? On the right side, see if you scale it up by a factor of 3, 3 times the distance, that factor 3 gets squared. So now m times 3r quantity squared, that's like 9mr squared, right? And then times 2 because there's 2 masses. Oh, that's like 18mr squared. You see the one on the right, it's like 9 times the inertia of the one on the left, right? Something like that, right? So yeah, so 9 times the rotational inertia, right? Harder to get it, speed up spinning, but also once it's in motion, harder to slow it down. Okay, let's look at a rotational inertia table. So for a single point mass, it's just mr squared, right? For a ring rotating about the central dashed line axis right here, it's really the same story. Like, what if you break this into like a billion different points? You say, okay, well, it's mr squared for every single point, so the aggregate effect is still mr squared. So those two expressions are identical. You see that? Right? But what if you have like different rolling objects or different spinning type objects? Right? There's different ways you can distribute mass, and there's some classic shapes that show up: solid cylinder, solid sphere, hollow sphere, or some of them, right? The thin corner on the edge you tend to not really see very often, but that's there if you need it. The solid cylinder. Well, think about this. If you break the solid cylinder into like a billion different points, kind of an integral calculus type thought process, right? And you do mr squared for every single point, right? Well, this r, if there's like one solid r associated with that cylinder size, not all the points are at that point, right? I mean, for the ring they were, right? But for solid cylinder, a lot of points are distributed closer to that central axis that it's spinning about, right? So the aggregate effect would have to be less than mr squared. And if you run the math on it, it ends up being half, right? Like half of mr squared is what it ends up being. Right? So if these two objects were like the same mass, and you were trying to get them rotating about, like each of those dashed line axes, right? Guys, which one would be easier to get rotating, the solid cylinder or the ring, given that they're the same mass? The solid cylinder would be easier. In fact, it'd be twice as easy because it has half the inertia in a rotational sense. Is that right? Actually, that solid cylinder is a really useful one. This is your turntable. If you just rotate this vertical, then your turntable is basically this, right? I mean, I guess it was more of an octagon than a circle, but pretty much this, right? Okay. The thin coin on the edge here, the inertia of that is like a quarter mr squared. That's probably never going to show up, right? By the way, all of these, your AP will not expect you to memorize anything from this table. If they want you to apply anything from this table, then they'll go ahead and give you the expression, right? But you should be able to apply it if they give it to you. Right? It's like, oh, like there's a string wrapped around the solid cylinder and it's being pulled, and right, the inertia is like 1/2 mr squared, or they might just give you value. They might say the rotational inertia is like so many kilogram meter squared, something like that, right? How about these really objects? We've got a bowling ball versus a basketball. Now the bowling ball is, I should say solid sphere, so it goes more physics term that you're a solid sphere, right? I think its mass would be pretty concentrated, probably kind of close to the center, right? If it's say like rotating around the central axis, right? Versus the basketball, or sometimes it's like a hollow sphere, or a what's the other term? A spherical shell. Sometimes you see that term, like a spherical shell. I'm approximating it with the basketball, right? It's like all the points are on the outside edge. Now, if these two objects, let's simplify a little bit again. Let's say these were like the same mass. Which one do you guys think? I've got the answer kind of covered up right now, right? Which one do you think would be easier to get rotating? The one where the mass is distributed close to the center, or the one where it's like more spread out? Which one's easier to get rotating? Yeah, where it's like closer to the center. It's kind of like these two, right? These two are kind of close, analogous, or these two are kind of analogous, or okay, right? Yeah, and you'd be exactly right. Yeah. So for the solid sphere, it works out to be 2/5 mr squared. For the for the shell, the spherical shell, it's like 2/3 mr squared. Right, right. Guys, 2/5 as a percentage, what is 2/5? Is that 40%? Right? And 2/3, is that like about 67%, something like that? Right? Okay. Now what about these 6 over here? Because you know what? If I kind of flip back the poster, I did kind of ignore, just to simplify this a little bit, the meter stick itself, right? But you could throw that in there. You could say, well, what if the meter stick has significant mass compared to these point masses? You want to also include that in the mix, right? Which I love that, right? But if you did, right? Like a meter stick itself, or just this pen I'm shaking back and forth, itself has rotational inertia. How could you quantify that? Well, if it's rotating about the center like this, which is the same thing as this, shake it back and forth, it's rotating about center, right? It's 1/12 ml squared. So if I know the length of this pen and I know the mass, 1/12 ml squared, boom, there you go. There's the rotational inertia of that, right? If I'm rotating it about the end, right, it's a lot more. Ooh, right? It's like 1/3 ml squared. In fact, if you know one of these, you can derive the other using something called parallel axis theorem, which is one of these other posters coming up recently. Okay, right, you guys good so far? Okay. Okay, so there's how much inertia has something like in a rotational context. Right. On to these ideas, a lot of stuff coming back today. All right, I'm going to do a little side thought here. I don't know if there's exactly a really ideal place for this, but here, just throw this idea out here and come back at some point, right? Center of mass. How do you figure out the center of mass of something? What's the significance or example of this, right? So in general, general way you can get center mass is you take a weighted average of all the mass bits. So you say say you break something into like a billion parts, right? You take each individual mass bit times its location, you add everything up and then divide by the sum of the total mass. They'll give you like an average location of the mass, which is like the center of the mass, right? So for example, what if I got like 2-point masses? What if these were stuck on a stick? I'm gonna stick a meter stick straight along this dashed line, right? Let's say the meter stick itself has negligible mass, right? I'm gonna figure out like, hey, where could I like balance this on my finger? That's one application of center mass. It's like, where could I balance it on my finger? Right? Now, if these were the same mass, it would just be the geometric center, probably right about here. Right? But if one of these is more massive than the other, it's probably closer to that, right? Well, this is exactly what this says. And here it is for like 2-point masses, 2-point masses. So like, these two right here, here we go, right? Mass times location plus mass times location. I'll divide by some masses to tell you for center masses. Right? Another application of center mass is like, I guess we're in projectile days. If you take a ball and like throw it through the air, it'll fall like a parabola path, like projectile parabola path, right? What if I take some funky shaped object like this right here, and I throw this through the air, right? Do you guys think every single point is probably just a little different as it's like tumbling through the air, doing something crazy, right? Like if you were a ladybug and you stuck like right in this corner, you were like along for the ride, right? You think you'd probably go like curly, 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 like so, something crazy, right? But there is one point on this that actually does follow a true smooth parabola. That's the center mass, which might not actually even be on the object. It's probably, I'm guessing, probably right about here should be the center mass of this straight object, right? I have a bunch of foam board cutouts. I'll probably have you guys do a mini lab one day where you figure out what is the center mass. One way you get a center mass too, like I mean, you could balance it on a finger, you could throw it through the air, see what point it spins about. Right? You could also like hang it from a string, and the center mass will always naturally hang like between where you're holding the string and the center of the earth. Right? So we did. Okay, so this is gonna show up at some point. I mean, maybe. I think it's good to know. Acknowledge that there. Okay, let's get back to the main story. I had to show you guys that at some point. So right here we go. Going back to the main story. Back to the main story. Right. So we're kind of picking up from this this rotational inertia table. Right? So remember, for a single point, it's mr squared. For some aggregate shape, it's well. Right, here's some that have been worked out by mathematicians. Right. But what if you want something that's not rotating about one of these predefined axes, right? Like a lot of these have like going through the center of the object, right? Like this basketball could be like spinning on your finger here, right? Right. But what if the basketball isn't like spinning on your finger? What if it's like rolling on its edge, which would actually be a different inertia associated with that, right? Something called parallel axis theorem. Now, all right, so what this is and what's the context for like AP, right? Right. So all this says is the rotational inertia is what it is, say like straight off that table, right? So for the basketball, just 2/3 mr squared, you can pull like right off that table. I picked a basketball, just random example. Right? So 2/3 mr squared for that spherical shell, right? And then plus md squared, where d is the distance to the axis of revolution, right? So that's where the term like parallel axis come from. So I got this axis of rotation, right? And then I got the second axis that is actually revolving around. And those are two different axes. Right? Okay, so I got these parallel axes, right? So then, okay, so all you do very simply is just add those together, right? The I naught plus the md squared, okay? Makes sense, right? And a really common application of this could be like a ball rolling on the floor, right? Ball rolling on the floor. It's not actually rotating about its own center. It's actually rotating about, here's like the pivot point down here, right? So yeah, you got the 2/3 mr squared of the basketball if it was rotating about the center, but there's another md squared, but the d happens to be the radius of the ball itself. That's why I can just go ahead and call that one r instead of d, right? Right. So okay, so it ends up being like this much inertia. So if you came along, like gave the ball a push, and you wanted to quantify it, I feel something resistance to motion. How much resistance to motion that is actually a bit more than it would be the ball like spinning about its own axis, right? Something like that. Okay, so what's the application to AP? AP, this concept did not make it into AP for you guys. AP is almost certainly not going to ask about this. Or if they do, they'd have to give you some context and set up the whole thing, which I doubt they would do, right? But what I've also heard too is that I think they're going to start including this next year, right? It's going to make it to the AP exam. So, if you're competing against like the next wave of students who are graduating and they do have this knowledge, then well, now you guys have it too. So that's good to know, right? I know I learned this back in high school and did this in college. Oh yeah, college, right? You go to college, really good chance you're going to see this. Okay, so you guys okay with that? I'd figure out rotational inertia. Oh yeah, notice I meant to mention about this too. here, go back to, let's take this basketball. Let's turn this into a wheel. If you guys imagine this could be a car wheel. Cars are driving along, got four wheels. Right? And how fast is any point on that wheel moving? Like, what if you were a ladybug and you stuck like right near the edge here, right? So you're going along for like, what would that feel like? Or how fast would you be going relative to the outside world at any point? Like the center of the wheel is traveling along with the car. Like if the car's going 60 miles an hour, do you guys think the center of the wheel is always going 60 miles an hour? Yeah, along with the car, right? Right. But right, let's go back to ladybug on near the edge of the tire situation. Right? What if you're right near the top here, this point, right at this moment? Guess how fast this top point is actually moving relative to the outside world? Double, like 120 miles an hour. You're right. How fast at this one instant is this point right here moving? Zero meters per second, 0 miles per hour, but only for like one instant, right? Yeah, it's get real weird, wonky type of motion, right? Right. Fun things to think about. All right, you guys ready for torque? Ready for torque? All right, so let's go. I'm going to flash back to this big picture roadmap from time to time. Okay, so we did inertia, but in a rotational sense. Okay, so go back and show us some questions about that. All right, now let's go to this next line. Now, let's see, Newton's second law of motion. Forces cause masses to accelerate. And then, Greek letter tau stands for torque. Or, actually, like two different expressions all shoved into one line here. I wonder what that's about. Let's take a look. So I have a couple of classic examples for torque. One you're looking at right here is a wrench, maybe trying to turn a nut. Let's say this rusted nut's all rusted over. It's been there since like 1940, and got to break the rust. How do you do it? So we put the wrench up to it. See, R cross F. Do you guys think? Do you think the longer the lever arm, do you think it's easier to get this going? Yeah, okay, because it has more torque. That's more turning moment. Moment is synonymous with torque in physics. There you go. Do you think the harder you push it, like bam, 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 the harder you push it, it's easier to break, right? And one more thing. You see that cross right there? It's actually a special kind of multiplication called a cross product, which means you only multiply together the perpendicular components. That's all that matters. Right? So if you push at some weird angle, only this perpendicular component, like perpendicular to the radial arm, right, actually goes into any kind of turning moment, right? Right. My other classic example for torque is opening a door. So I'll walk over and do a live demo for you guys. Every time you open a door, just think how that's going to feed to open the door, right? Well, I got hinges here, and here's the handle, right? Oh, why not push really close to the hinges? Is that really hard to open the door? That's really hard to open the door, right? If I push to the center, that's a little easier. Right? Hey, why is it that the handle is always opposite the hinges? Right? Because now it's really easy because I get like a bunch of radial arm. There's my turning moment, right? Notice I'm pushing perpendicular, right? What if I push and pull parallel to the door? Is this ever going to open the door? No, that's never going to turn the door, right? Not pushing like parallel to the door, right? Okay, so yeah, only the perpendicular component actually does anything, right? If you want to maximize your torque, maximize the R, maximize the F, and also make it perpendicular, right? Okay, you guys got that? Now, careful too, if you ever open up a physics textbook or maybe get an AP question where they give you this angle right here, because if they give you this angle, this is no longer sine, it's now what? Cosine, right? If they give you this angle here, now my picture, it matches up with the sine. Okay, that's got the picture, right? Now, what I haven't mentioned yet though, is this green box, I times alpha. What's that about? So I want to give you guys a real classic example here. Right? It's one of your thumbnail notes. Yeah, there's a really good chance you're going to get some question on the AP exam that links exactly back to this picture, whether it's multiple choice or FRQ. Right? What if you have your turntable, and I'm going to wrap a string around this turntable? See that string all wrapped around? Right? Okay, so it can spin around this central axis, and then pull a string. Right? Now, if I pull with a constant force at this constant radial arm, that's R cross F, that's a torque, right? Do you think this turntable is going to speed up spinning? Speed up spinning, right? That's an acceleration. That's angular acceleration, alpha, right? Well, how much is it going to speed up spinning? Well, let's see. I have to know what's the resistance to change in motion. That's something to do with inertia. That's a rotational inertia. That's I, right? Now, if this was your turntable, I could probably go back a few slides here. I could probably approximate that turntable as like a solid cylinder is probably pretty close. I'd say 1/2 mr squared. So if you know the M and you know the R, put it all together and get how much inertia, right, in the rotational sense, right? Again, AP is never going to expect you to memorize that. If they want you to apply that, they would have to give that to you. Yes, right. So that you can figure out. Right. But here's where it all comes together, right? That R cross F, oh, and those are always at 90 degrees to each other, like conveniently for the setup. That's why I like the setup too. Whatever direction you pull the string, it's always going to be conveniently perpendicular to that radial arm, right? Right. So sine at 90 degrees, just one. Don't even think about it, right? R cross F is torque, but I times alpha is torque. You can set those equal to each other, can't you? Right? That torque is equal to that torque, right? I times alpha. You guys see where this is going, right? If you know any three of these or can figure out any three of these, then you can solve for the fourth one, right? If you know bam, bam, and bam, you can solve for bam. If you know bam, bam, and bam, you can solve for bam, right? Knowing three, you solve for the fourth, right? And then, of course, you can always get your classic proportion questions too. Like, what if you doubled the something? How about that? Do something else, right? Okay, you guys got that here? Right, there you go. Right. Right. Okay. So there you go. So torque is R cross F, but torque is also I times alpha. Right. And see it right here. Right. Right. Now I haven't mentioned this peak box yet, but I'm not quite ready for that. But that'll come back later. Right. It's called angular momentum. It's something to do with like inertia motion. Right. So see where we are on our checklist. We're still on torque. There's some things I still want to tell you guys about torque. We're still here, but working our way down. Right. Okay. Let's get a step more abstract. You guys ready to get a little more abstract right here? So, gonna stay on the slide for a moment. Ask you guys this. Hopefully, this will be an obvious question. Maybe I don't know. Right? As you guys are seeing this, so here's rusted nut right here, trying to break the rust. Bam, bam, bam. Right? It's like finally get this move. Right? Guys, is that as shown? Is that a clockwise or a counterclockwise torque? What is that? Counterclockwise. Counterclockwise from our point of view. And that's as far as AP will do it. AP just goes with clockwise, counterclockwise. Right? Here's the thing, though, is that's kind of a matter of perspective. Like, what if I do this? What if I lift up this paper and somebody walks behind this paper and looks from the other side? Right? Now, can you guys think real abstract from the other side what this would look like? From the other side, this looks like what? Clockwise or counterclockwise? Clockwise to them. Now, it's still counterclockwise to us, but it would be clockwise to someone on the opposite side. If you step behind a clock, okay. See the opposite. Okay. So what direction is this really going? Well, you have to stand in a certain position to get a certain perspective. There's no like mathematical absolute answer to that, or is there? Right? There is one perspective that you can do that like everybody would agree on the direction of torque. The trick is you have to open up a third dimension. You guys see like this has all been a two-dimensional concept so far, right? I got an XY plane right here with the paper, and counterclockwise is on that XY plane, right? So there is a way you can define this where everyone will agree the direction of the torque, right? It's something called right-hand rule. Right? So you have to use the right hand, otherwise you get everything backwards, right? If you point your fingers in the direction of the radial arm, or so this could be the rusty nut here, and then here could lead out to the wrench, right? Or this could be the door hinges leading to the handle, could be out here, right? Here's R, right? And I curl my fingers in the direction of the applied force, then my thumb is going to point like out of the page. That's like a third dimension, right? Out of the page, right? And whether you do this in front of the wrench or behind the wrench, everybody agrees. Right, here, just right here. Here's R cross F. So my thumb is pointing out of the page, right? That would be called a positive torque, right? And even if I did this on the other side, I would still get the same answer, right? So it's positive. So kind of you think sort of this way, like counterclockwise torque kind of is a positive torque, right? If I did R cross F this way, my thumb would point into the page, that'd be like a negative torque, right? Now, AP doesn't go that far. AP doesn't ever mention right-hand rule. But if you go to college, there's a good chance you're going to see that. So maybe good reason to know that. All right. Another detail that kind of links to this too. Did you guys in a math class ever learn matrices? Do matrix? Yes, you guys did. That's the first yes I've heard all day. Oh, all right. Caught by surprise, right? Yeah. Okay. So if you've never done matrices, then well, if you do see this here in college, there's a good chance that your college instructor is going to pull up matrix math and solve this with matrices, because now you can have torque like in any like three-dimensional grid, and you can have like going to some like 31-degree angle, or something crazy, right? I might pull up a video demo one day, right? Yeah, if you've never seen that before, I'd be good to give yourself a crash course one day if you happen to run into this in college. That's a little bit beyond the scope of even AP physics, though, but good to know that's there. This looks like. Okay. All right, one of the labs we're going to be doing probably next week is figuring out what's the rotational inertia of some like crazy PVC pipe system. How this PVC pipe that looks like a T shape and it's got some masses and crazy going on. Right? It's pretty free to rotate about this central vertical axis, kind of free to rotate like this, right? But if you put your hand on, you can feel how much resistance to change of motion, how some inertia. If you took some lab masses and like tagged them right here, I bet you would feel like a different resistance to change in motion, right? Hard to get it going, and once it's going, kind of hard to stop it. Right? Reverse, right? So how much rotational inertia? And the process, I just want to play with this idea today. Just have a few days to think about it, and next week we'll probably do this, right? This is really closely related to this side here, right? So R cross F is I times alpha. And what's the technical setup going to be? Something to do with this, right? What if I wrap a string around the central axis, which has a radial size? That's a small r, maybe it's like a centimeter or two, a couple centimeters, right? Right. And then the string has a tension in it. Hey, there's R cross F. You guys see some R cross F, right? There's a torque, right? Now, where's the tension coming from? Well, there's some lab weight hanging over here of this pulley. The tension is probably going to be a little bit less than the actual weight itself if it's accelerating down very slowly, right? Kind of close, but not exactly, right? You guys remember that from Atwood days, right? And then, okay, so you can also do some kinematic motion, maybe bring along a stopwatch and figure out like if this thing starts from rest, like how many revolutions or radians is it doing, so much time, blah, 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 right? You can figure out what is this alpha, which is a kinematic concept, right? So you guys see how this is all going to fit together, all the puzzle pieces, right? R, measure it, bam, right there. F, that's the tension string. It's related to this weight. Do a little bit of physics digging. You get, bam, got that. Right? Kinematic motion, bam, get that. You can solve for what's the resistance to change of motion. What was the rotational inertia thing? Okay. So that's a future fun adventure right there. Think about that one. Equilibrium. So you guys have solved equilibrium problems. Let me show you guys an old example of that, and then we're just going to add on to this. Do you guys remember an old example? I think this one was in your book, I think, right? Does this look familiar? If there was like, I think it was like a lantern or something hanging from a string, and the string like split like this. Oh yeah. You guys remember that one? That was like way back in. It was Unit 2 by our book, right? AP's book, right? And the question, like, what was the tension in each string? Now the bottom string, it's easy, just going to match the weight itself, so that right, zeroes out equilibrium, right? But each of these top strings, well, it depends what these angles are, like alpha and beta from like these dashed line vertical axes, right? And the way we did this, we set up a system of equations. We said, well, if you split this into components, oh, I forgot I had this poster ready to go. Here's my nice version of it. There we go, right? If we split this into components, in the x direction, it has to zero out, and in the y direction, these two up and this one down also has to zero out, right? So that was the setup. System of equations, two equations. That was way back in the day, right? But now we're going to add to the story because there are some equilibrium questions where, well, that's not sufficient to answer. And I've got some posters coming up where you guys will see this be the case, right? You have to bring in a third condition. So there's one more condition for equilibrium. That's the torque also has to zero out. You don't want there to be any turning moment. Right? Now in 2 dimensions, it's just those 3 conditions. Boom, boom, boom. Okay? If you opened this up to 3 dimensions, now you got 6 equations. You might have like a 6 equation system of, system of equations, right? 6 equations, right? If you're doing civil engineering, you're designing a building, designing a bridge, designing blah, 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 right? Some truss structure, right? You need to check all 6 of these conditions to make sure that they'll make like static equilibrium, right? Then make sure your materials have the correct strength and correct diameter, blah, blah, blah. There you go. Right. So, and then in this class, we'll mostly stick to just like 2 dimensions is what we're looking at, some kind of plane going on, right? But a bigger context if you're an engineer one day, you think about 3 dimensions. Right, let's look at some examples, and I've got maybe like a 2-part lab coming up with the torque that involves this too. So you want some equilibrium situation. Let's start with the seesaw. Have you guys played on a seesaw? You guys played on a seesaw when you were kids? Yeah? I think they're phasing those out. I think they're getting rid of those on playgrounds. It's like not safe enough for the 2020s or something. But here, I guess we're all old enough to remember the good old days. We could play on seesaws. And now, if you and a friend get on a seesaw, and let's say you're like the same mass, the same weight, probably sit like equal distance from this pivot center, and then it kind of balances out. Well, if you're not the same weight, probably the heavier guy sits closer to the center, the lighter guy sits further from the center, right? Okay, and so you can still kind of balance it out, right? That is torque going on right there. That's torque equilibrium, right? So we're going to start kind of basic, which is this poster, and we're going to get more complicated. We're going to build on this. Okay, so you guys ready to start on the shallow end and then go to the deep end, right? So the torque has to zero out, right? And I'm going to pick this central point as the pivot point, right? There's a reason I got that kind of in quotation marks, right? And say, okay, what's the R cross F going on, right? So I got this radius 3x, and then F is mg, so there's 3x and mg. That's going, it looks like counterclockwise. right? That needs to balance out with this clockwise torque over here. The radius is x and the force is 3 mg. Okay, and okay, so say to do a minus because clockwise, right? That needs to zero out. Well, I obviously set it up to zero out, right? You guys see that, right? If one of these was a mystery weight, like what if what about this? What if like, hey, I know what my weight is. My weight is 75 pounds. What's your weight? I don't know what my weight is, right? It's like two kids talking to each other, right? Well, all they have to do is like go up to a seesaw and then like slide around until they balance it out. And then they can set this up and solve for the unknown weight. You can do this too. I've done this a lot of the times in this class. Like I'll have something back in the lab area and there's like no digital scale back there. And I'm like, what is the weight of this thing? So, okay, well, I've got a meter stick within reaching distance. I can like throw this on a pin so I can like balance on the 50 centimeter mark, right? I take some known quantity, like this guy is 200 grams, like set him up here, boink, right? And then take my unknown quantity and like slide it around until it like balances out. And then you just like, do a little bit of, slide around, divide, boom, you got the unknown weight. Right, you guys got that? Right. All right, so are you guys good with that? Is there any question about that so far? That's all right, right? That's okay. Okay. All right, you guys ready to get a little bit more conceptually involved with this? Okay, so still same thing. You might notice if you've been watching real close that I've actually left off some information here. Notice I did not draw the upward vertical force from the pivot. Do you guys see that? Do you guys think there's an upward force right here? An upward force from the pivot, right? Now, my particular setup, I just ignored it because it provides no torque about that point itself. Kind of like if I press on the door hinges. Here I'm pressing on the door hinges. Is this ever going to turn the door? No, because there's no turning moment. There's no lever arm. Sometimes it's good to set up a problem like that where you zero out some like unknown force. Right? In this case, you guys see something like that pretty soon. Right? Do you guys think this upward force has to be at least 4 mg, right, to carry all this weight? Right? It would just be 4 mg if the mass of the plank itself was negligible, right? If you include that weight also, it's probably a little bit more than that. Okay, something like that. Okay. This torque equals 0 Newton meters, or the American equivalent is foot pounds. If you ever hear foot pounds, foot pounds. Ooh, but we're doing metric, right? Newton meter. You don't actually have to pick any special point to sum the torque about. You can technically pick any point. I can pick this point. I can pick this point. I can pick this point. I could even pick this point right here. That's looks like it's off the entire system. The torque still sums to 0. Now, it's kind of an abstract idea, but you could show that that's still the case. Now, this particular setup is probably the simple setup because I picked the obvious pivot point to do that. Okay? But if I picked any other point, I would have to include this like 4 mg going upward, and this would still zero out. Okay, all right. All right, you guys ready to go a step deeper? Step deeper. Right. Now, this is like a seesaw, right? You guys see a seesaw, right? Right. Let's do the scaffolding. Here's the scaffolding, right? And I built this in class. Maybe it's a good idea to see this in class. Do you guys see it in the center of the room in the back? Oh, I built that this morning. Oh, yeah. You guys see a couple of spring scales right there. There's like a lab weight right there. Hey, and here's exactly the same. Here's like the cartoon version right here. Right? Maybe I should go and add some spring scales right here. Like the left tension and the right tension. That's what TL and TR are, right? Left tension, right tension, right? Right. All right, so to tell you guys a story with this too, right? You guys remember Paul Hewitt? It's that guy sometimes will show you has like 1-2 minute demos, right? He has an interesting backstory. So he graduated from high school, didn't really know what he was doing in life. Worked a bunch of odd jobs. He was a boxer at one point. People punched him in the face. He had this job painting signs. He was like painting billboards. He was up on the scaffolding, and he worked with this guy named Bert. And they would talk about physics, except they didn't actually really know much of what they were talking about because they'd never really been to college or had that education, but they were curious about the world and they asked each other questions. So they're walking around the scaffolding, and like Bert one day is like pulling this scaffolding rope, so like boing, 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 right? And Paul Hewitt's over here saying, "Hey, Paul, like come over, walk over close to me." So, okay, so he walks over. He's like, "Hey, here, boing, 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 boing." Right? Ooh, I wonder how the tension of this is changing as a function of like where I'm standing on the scaffolding. It seems like the closer I stand to the right, the more this tension is going up. That kind of makes sense, right? Right. And then I wonder, like, I wonder if the amount that this tension increases exactly matches the amount that this left rope would decrease. Do you guys think it would? Yeah, because that would match this, the sum of the forces vertically goes to 0, which is something you guys learned like 2 months ago, right? Right. These upward forces and these downward forces have to balance out to 0 newtons, right? But what if you want to figure out exactly what is the tension in each of these 2 ropes? This sum of the forces goes to 0 is not enough to answer that question by itself, because now it also depends where you're standing. the closer you move this, if you nudge this weight to the right, yeah, these tensions change, right? So the other condition that you need to answer that question is the sum of the torque goes to 0, right? Now, this particular equation that I set down here, I was trying to pick kind of easy one, right? Well, if you're going to solve this all with one equation, which you can do, right? Notice that there's two unknowns. You don't know either tension. Hey, do you guys think if I pick one of these points as the pivot point, right, that the torque from that very force would cancel out, so 0 out, and then I could just solve for the other tension, which is exactly what I did in the setup right here. I picked this point as the pivot point. I could pick any points there. This could be the pivot point. This could be the pivot point. This could be the pivot point over here, right? I picked this point right here. And I like that point because whatever the tension on the left side is causes 0 torque about that point because it's like pushing on the door hinges itself, right? Ah, here's R cross F, 0 distance from the left tension, right? This says that, right? Now everything else is kind of locked in place, right? The weight of the beam, the weight of the beam itself is distributed over the entire thing, but it's okay. It's perfectly fine mathematically to make believe that the entire mass and the entire weight of the beam is at its own center of mass, which is what I did right here. You see, I've got the entire weight of the beam at L over 2, as long as this weight is distributed evenly. Right? Here's L over 2. Right? Guess yeah. Right? Right. Oh, it's negative because clockwise torque relative to this point. If I treat this point, this pivot as like a door hinge, I see the weight of the beam is trying to make the whole thing turn clockwise from our point of view. Right? The weight that's stacked on here is also clockwise. So here's the weight. Here's some distance x. Here's R cross F. You see R cross F. Also clockwise, that's why mine. Right? And then the only thing holding everything in check then is this tension on the right side. Here's this R, which is now L, crossed with this force, which is now the tension on the right side. Right? You guys see how there are two unknowns here. I don't know the two tensions. But I know everything else. I know these weights and these locations, blah, 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 right? There are two unknowns, but this one zeroes out, which means that with this one expression, I can solve the tension on the right side. You guys see that? You see that? Have you guys do something really similar in an upcoming lab, probably in a day or two. Okay, you guys think you can navigate that in a lab, right? Right. So you guys see two of these equilibrium type situations. You guys see the seesaw. You guys see the scaffolding. Okay, right. And I might give you guys both lab. Oh, here's some lab setups. I keep redesigning this every year, but here's the seesaw version. Spring scale, like single pivot point seesaw. I bet the torque you could show would 0 out. I bet if I give you a mystery weight, you could solve for what is the mystery weight, right? Right. So like have one of these like covered in paper somehow. How much is it? Right. You could probably set up so it balances out. Right. How about the scaffolding? Right here. It's a new lab table. Oops, I should. Right, in case you missed that, you got to see a transition. I got 2 different torque labs. Probably need to give them different titles or something. Here's the scaffolding version right here. Right. You guys think the same thing? Like what if I covered up one of these spring scales and I asked like, hey, what's the reading of the spring scale? Or what if it was a mystery weight or something like that? Or what if the question was like, where is the weight located? Right? If there's enough information, you could figure out whatever you don't know. Right? All right. Good so far. Good so far. All right. So move on to a new concept called angular momentum. Right. So here's back to the big picture checklist. Right. I talked a ton about torque. Right, R cross F, I times alpha. Right, right. Now let's go into the momentum version. Right. So back before the break, you guys saw momentum was mass times velocity. Now we're going in a rotational context. So that's capital L. This is angular momentum. So it's momentum, but in angular context. It's rotational inertia times angular velocity. Okay, so you guys see how that's analogous, right? Now, momentum was a vector. Angular momentum was also a vector. Momentum was conserved in closed systems. Angular momentum, do you guys think it's also conserved in closed systems? Yep, it sure is, right? And that's what this says right here. So angular momentum is I times omega. And oh, look at that, it's conserved. The angular momentum initial equals angular momentum final. You can use this to solve, well, remember in a linear context, it was collisions. So I guess like some sort of analogous stuff, right? My classic example is the ice skater, right? The figure skater. You guys ever watch figure skating, let's say like Winter Olympics, and you guys see a figure skater like go into a slow spin and then they pull their arms in and speed up spinning? You see that? Right. This right here is the classic physics example that I have a video demo this too, but I'll probably show you guys another day. Right. So they go into a slow spin, right? But they've got their arms like spread out. That means their mass is distributed like really far out relative to the central axis that they would be rotating about, or that they are rotating about, right? So they have a huge rotational inertia. and a small angular velocity. They pull their arms in, which takes work. It takes some force times distance. Pull your arms in. You guys think that you're converting chemical energy from your muscles into mechanical energy, like kinetic energy? You guys think? Ooh, great, because your work, force times distance, right? And then zoom, speed up spinning. Now, what's conserved, and you can solve and figure out like how fast you're spinning, right? Is this angular momentum. So that's I times omega. So do you guys see if by pulling your mass in closer to that central axis, you decrease your I. Therefore, omega is forced to increase. Is that so? So that product is conserved, right? So there you go. There's conservation of angular momentum right there. You guys got that? Okay. Which is the pink box that I skipped before, right? Remember, you guys remember this? So remember the string wound around the turntable, you pull, a torque causes the thing to speed up spinning. Right? Now, at any particular moment, maybe it's rotating at some particular angular speed, right? And okay, you have some rotational inertia for the turntable, right? Multiply those two together, you get angular momentum going on right there. Right? Guess that. Right? Actually, I meant to say that. I got another thing I'm going to show you guys. Now let's do this next. I'm going to swap these posters. Right? The next thing I want you guys to see is the connection between torque and angular momentum. Right? You guys see torque? Right? You guys see this pair of graphs? Right? We've got torque versus time and angular momentum versus time. And the story that you can attach to both of these graphs is this right here. Right? Got my string around my turntable, and zoom, I'm pulling with a constant force and a constant radial distance. Isn't that like a constant torque? Right? Guys, these two graphs right here, you will see both of these graphs on the AP exam. This is probably several points on the AP exam, just in that one poster right there. It's probably several points on the AP exam. This right here could be the difference between passing and failing. This one poster right here, right? Okay. And these two are part of the same story. So it's two different perspectives, two different graphical perspectives of the same story. So I'm applying a constant torque to that turntable, I'm just pulling that string, and it's speeding up spinning, right? So the increased angular momentum is this increasing size of the green rectangle. Is that rectangle? Delta L, it's like, and then the whole rectangle would just be L, right? Okay. And then what about an angular momentum versus time perspective? Okay, well, angular momentum is increasing because the size of that rectangle is increasing, right? It's increasing at a constant rate, and that constant rate is torque, right? So you guys see that there's kind of a calculus relationship between these two, right? Right. The integral of torque versus time is angular momentum. The rate change or derivative of L versus T is back to torque. Right? That's it too. Right. Oh, how about a point mass? Right. What if you this right here is always AP always likes to ask this question. So this is probably going to be a question. This might be your FRQ, right? What if you like throw an object at like a swivel stick? Here's my swivel stick. You guys see this X up here? It's like a pivot point. You guys see it can like swivel around this point, right? And maybe this point mass collides and sticks inelastically, or maybe a boing bounces off. There's different variations on this, right? But usually the question goes some version of like, how fast does this thing get rotating? What is omega like post collision, right? Okay, well, collision, something to do with momentum. It's rotating, angular momentum. What is the angular momentum of like a point mass? That's a really bizarre question. Well, there's an answer to that. You can like derive this and prove this, but it's probably a good idea to memorize this. Can you guys memorize this? Because you're going to be asked a question about it. AP always likes this question, and it's not on your equations. So the angular momentum associated with the point mass is regular momentum, mv, times the radial distance from the center. Okay? I guess that. You know what? We're about to run to the bell, so let's look at these real fast. Here's spinning a basketball. Here's rolling downhill. Here's rolling downhill again. And here's a roll race. We're going to have to save those for another day. All right. You guys have a great rest of your day.